Lab 6, Faraday's Law. The purpose of this lab is to analyze a magnet falling slower than expected in a conductive tube, and determine how change in magnetic flux creates a force which opposes gravity. In this lab, I dropped a small bar magnet into a conductive tube of aluminum foil, noticing that it takes significantly more time to fall than a non-magnet. I then created a computational model to simulate the flux, slowing the magnet down. The two fundamental physical principles are magnetic flux, which is the double integral over a surface of B dot dA, and Faraday's law, which governs how an EMF is created with a change in flux over time. The negative sign in Faraday's law just means that it opposes the change in flux. So we usually use the absolute value of the EMF and then figure out d phi dt with the right-hand rule. In the experiment, the system was the small bar magnet, the surroundings were the conductive tube, the air, and the hand. The length of the tube was 0.0454 meters. The width of the foil is 0.005 meters. And the mass was 0.0028 kilograms. In the experiment, we dropped the magnet from the top of the 0.454 meter tube and measured how long it took. We did 5 trials with these times. The average was 1.2 seconds. If gravity was the only force acting on the magnet, we would expect it to fall 0.454 meters in 0.3 seconds using kinematics. Therefore, there must be a magnetic force due to change in flux. This is the code for the computational model. Then interpreting the simulation. The intensity of the coloring in the tube indicates the magnitude of current, which colors corresponds to clockwise current. Red means positive current, which corresponds to a positive EMF, which means that the flux is negative, which means the B field created is down, which means that the current is clockwise. Blue means the opposite. What happens to the dynamics of the system when you flip the magnet around? It still goes the same slow speed through the tube because the change in flux is still opposing the magnet's fall. How does the total time in tube of your real-world system compare to that of your computational system? How might the computational system be made more accurate? Experimental system time is slightly less than computational time due to errors in timing, possible air resistance, or miscalculation in the model. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? The VVT graph increases up to a terminal velocity, which implies that the magnetic force is proportional somehow to the velocity of the magnet. If the resistivity of the conductor were reduced as close as possible to 0, the magnet would fall slower. The induced EMF would remain the same, but the induced current would increase because current is EMF over resistance, which produced a larger induced B field, a larger magnetic force, and a slower terminal velocity. If holes or slots were cut into the tube, it would interrupt the current flow and allow the magnet to fall faster due to a smaller induced B field from a smaller force. In this lab, I analyzed the effect of Faraday's law on a bar magnet falling through a conductive tube. I measured the time it took for my magnet to fall and compared that to my computational model.